So one example from class was understanding why polar graphs look the way that they look. So we plotted this polar graph of sine 2 theta, and we said, oh, 2 theta has 4 petals. I wonder why that is, and I wonder why they happen where they do, and why they have the shape that they do. And then we noticed that with 4 theta, we have 8 petals. So 2 theta gives you 4 petals, 4 theta gives you 8 petals. Why is that pattern happening? And then 3 theta gives you 3 petals, not 6. So why is that pattern happening? All right, well, how can you use what I just described to answer this kind of question? 2 really great problem-solving strategies you can use are connecting to another representation. So if you just stare at this equation and kind of hope that an idea is going to come to you, that's not really how problem-solving works. You don't solve problems by staring and hoping an idea comes into your head. You got to try things. You've got to get things on the paper in front of you before you can start noticing what connects to what. So let's compare this polar version to the rectangular version, and let's kind of interpret corresponding parts of the equation in the same way. So here we can interpret x as being the angle and y as being distance from the origin, which is what they mean over here in the polar version. And now you can start noticing some similarities. Over here, it's familiar that the range of sine goes from -1 to 1, and here you're noticing, aha, this distance is 1. So the furthest away, or the furthest point of all of the petals is a distance of 1, and it's not an accident. It's because it's coming from the sine function over here. A couple of groups were sort of conjecturing, wait, I see 4 petals here, and I see sort of 4 humps there. So they were seeing maybe a connection, but it was fuzzy in their minds, because here some of the values are positive and some of the values are negative, and kind of how does that correspond to the 4 petals over here? So a great thing to do is to try and add more features to try and see which features match up. So I've written that here as think about the process behind the algebra. And we'd said that the process for plotting polar was to imagine plotting individual points as your angle gets bigger. We had sort of a data table where you start with a small angle and you make it larger, and you use the equation to figure out what the radius is. But this is telling us those values. So instead, let's make more connections. So from here to here, this is pi over 2. So this is like the first quadrant. This is 0 degrees to 90 degrees. And so as my angle goes from 0 to 90, the distance goes from 0 to 1 and back to 0. And so that's why we see, I'm going to draw a bunch of lines here. That's why we see as the angle goes from 0 to 90, you see that the points along that line go from a distance of 0 at the origin all the way out to here, where the distance is 1 when we're facing at 45 degrees. And then as the angle increases, the distance along the line goes all the way back down to 0 again. And so that way of thinking can start helping us piece together what's happening. Because just looking at this equation, you might expect this is the way you draw it. You might think you go boink, 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 boink. But if you really pay close attention to the connections, between 90 degrees and 180 degrees, all the distances are negative. So what that means is when our angle is facing in this quadrant 2, the distances are negative, which means you're actually plotting the points in the reverse direction. So if you're increasing the angle, you don't draw this petal first and this petal second. You draw this petal first and then this petal second, and this petal third and this petal fourth. And you can get all of this yourself just by thinking very carefully about the meaning of the algebra and then making connections. And the more features you can identify and the more detailed you can be, the more likely you'll see a connection that's helpful. Another example is the one that I showed you in class yesterday, but I thought maybe it would be nice to do a video of it. It was the test question where you're trying to describe the position of the dot in the Google app timer, the Google Timer app, where you type in a certain number of seconds and then the dot slowly moves in a circle as your timer counts down. So this is a great problem. Well, all right, so step back. If you want to practice the skills, go ahead and think about what are the basic things you know how to do in the unit, and then what are your problem-solving techniques, and think about what do you think might be appropriate here. So you can pause the video, give it a try. So for me, my top picks were writing what you know and what you want to know using math notation, solving the problem one piece at a time, because it turns out there's a lot of pieces to this, and then using other representations to be really clear in your own mind about what you know and what you want. So I know I want a circular motion. So if I'm just kind of, brainstorming, if I'm sketching, I know one of my basic ideas is if I've got cosine t sine t, I know that produces a circular motion because it's a length 1 vector centered at the origin that's just rotating once every 2 pi seconds, if t is in seconds. Okay, so the question is, how can I take this basic circular shape and make it fit this problem? And so I'm going to notice a couple differences. Well, one difference is this traces out a circular motion where the path is radius 1, because this vector is length 1. But here the vector isn't length 1. It's the radius of this circle is larger. So I know I'll need to scale it on the outside so it's the right size. And another thing I know I need to change is I need to change how fast it's doing the rotation, because here I need it to take s seconds to go up 2 pi radians, whereas here, whatever time it is being interpreted as the angle. So if time is 2 pi, that means that it has gone a full circle already. So the other thing I'll need to change is the angle. Is there anything else? Oh yeah, where it's centered. So this is tracing out a circular shape at the origin, but I know that I need to move it up here. And so each of these is a basic skill we've done. We know about how vector addition, you can think about it as putting the vectors head to tail. And then that makes it really easy to translate a vector that's moving to a new location. So let's start sketching out these various ideas. I think I want a vector that's taking me to the middle here, and then another vector that's rotating. So I'll have two vectors. I'll have this A, and I'll have this rotating vector B. So my A vector is going to take me to the center, and then I'll have a B vector, which is going to be cosine something, sine something. And then I also know that I need to scale it to be the right size. So this is giving you a template. All I've done is I've written down what I want to know by thinking carefully about all the pieces. And so now I can start tackling these pieces one step at a time. Like, how do I actually move it to the middle here? And then what size should it be? And then how do I think about the speed? So the information that's given doesn't quite tell us everything we need, but hopefully it's easily calculated. So halfway between 90 and 320 was, I believe it was 205. And then this radius is 115. And again, you can do that sort of basic arithmetic. So if I'm going to go to the middle here, that's an x displacement of 205 and a y displacement of 400. So I've found that part. And then I know that my radius here is 115, so I'll scale my vector by 115. And then the last part I want to really focus in on, it might be hard for you to think about how to jump directly to an equation here that fits the situation. So this is where I like to use other representations. I think very graphically, so I like to draw little graphs. You could use a table either way. But it's like, I know I'm going to have some expression with t inside here, but when I plug in a particular time, I need my math expression to give me the angle I want. So we're really describing a function where the function's going to take time as input, give angle as output. So you could think about representing your function this way, time, angle. Or I like to do it graphically. So this is time and the output is angle. So what do we know? What do we know about the problem? Or I guess you could think about it as what do we want to have happen? So I said that at time 0, we need the dot to start out up here. So that's an angle of pi over 2 radians. So in a table, I could say time 0 must be pi over 2 radians. Or in a graph, I could say time 0 must be pi over 2 radians. So I know, and again, what we're doing is we're trying to think about what function should we put inside here. But we're representing the function not algebraically, we're representing it using these other tools, so that'll help us think about what the algebra should be. All right, so what else needs to happen? I know that it needs to go 2 pi radians. It needs to go all the way around in s seconds. So you could think about it this way. In s seconds, I need to go pi over 2, plus another 2 pi radians. So this would be 5 pi. Nope, that's wrong. It would be 5 pi over 2 radians if you were going to combine those together. And then same thing over here. After s seconds, I know I'm over here at pi over 2 plus 2 pi. All right, so I've represented it. Now all I have to do is ask, what's the equation of this line? What's the equation of this function? And you know how to find the equations of lines. So it's got a y-intercept of pi over 2. The slope is rise over run. So the rise here is from pi over 2 to pi over 2 plus 2 pi. So it's gone up by a total of 2 pi radians. It's gone over by s seconds. So rise over run is going to give us 2 pi over s. And that's the slope. So that's the coefficient for my independent variable t. So this is the equation that describes the relationship I want. And so that's exactly the equation I'd want to plug in here, because this equation lets me plug in a time, and it will tell me the angle that my point should be at. So you can see that there's a lot of steps here, but each step is connected to the other things in the problem. And that's what I want you to be focused on, is how can you use the basic skills you have and tools like graphs and tables to think your way through the problem step by step.